Hello. In this video, I will go over the homework covering the material reviewed in lecture 0.34 called Infinite Arithmetic Approach. And as always, I hope you watch this little video. And to summarize the video before we start the homework, the idea in the video is very simple. If you have a limit of a function as function approaches to some target value, your first instinct should be to throw the target value inside the function and try to figure out what's going on here. And if the function is continuous, then you will simply be able to compute the output of the function, and that's going to be equal to the limit. If the function is not continuous, you can still figure out the limit using what's called the infinite arithmetic, that is when you have 0 and infinity, and while initially the expression may not be well defined, you can use a bit of analytical skill there and still figure out the limit. So, for example, infinity plus infinity doesn't have to be well defined in order for us to understand that it's going to be infinity, unlike infinity minus infinity. So, altogether, we learned that there are 7 unresolvable indeterminate forms. I'm going to list them all here, but you can see them all on the left. So if you have one of this, that means you have to be a little bit careful, because any one of these indeterminate forms may result in any answer. That is, I can give you a problem of type 0 to the power 0 that has the answer 5, or the answer infinity, or the answer negative infinity, or the answer 0. So this type of problems require special attention. Some of them we learn how to solve analytically, but in the near future we'll learn the most universal approach to all of them, called L'Hopital's rule. But before then, we just have to learn how to deal with it. And some of these limits are too basic that we just call it special limits. So, for example, limit of sine of x over x as x approaches to 0 is equal to 1. Although, if you plug in 0, initially you'll get 0 over 0, but the limit is equal to 1. And another special limit that you'll need to know to be able to do the homework is this one, 1 minus cosine x over x. This limit initially is also of type 0 over 0, but this limit is equal to 0. And it's very easy to visualize this, what we call special limits. We can just use Desmos, and we can graph the function sine of x over x and look at it around 0, and we can clearly see that the limit is equal to 1. And we can also graph the function 1 minus cosine x and divided by x, and we can clearly see that that limit is equal to 0, although neither one of these two functions is defined at 0. It's undefined, and this one is also undefined, but the limits do exist, so we call them special limits. And again, the idea is simple. You got the limit, you plug in the target value inside. If you don't have any zeros or infinities, you just figure it out. If you have 0 and infinities, you can still figure it out, unless it's one of these 7 indeterminate forms. And along the way, if you ever have to use one of the special limits or another one, you do that. So this is what I refer to as infinite arithmetic approach. So let's go ahead and start the homework. And let's see what we got here. And by the way, I have to give you this little disclaimer, Newton didn't have too many good problems to practice the true infinite arithmetic, so I put together whatever Newton had, and it may not be the best representative of the concept presented, but we'll work with what we have. So let's get started. We have a limit, and even though it says use the limit loss to evaluate, use the limit loss is just a fancy way of saying plug the target value in. And the limit laws basically say if you have a continuous function, the limit can be passed through the continuous function, or in other words, the continuous function can be factored out of the limit. So rational functions are continuous in this case because the only place a rational function is discontinuous is when the denominator is equal to 0, which is not the case. So again, we can learn that by simply throwing 1 inside of the function. And as you can tell, we're not having any issues here. We have 3 plus 5 in the numerator, and we have 7 minus 3 in the denominator. So the final answer is 2. Great job. And again, if you just follow all the suggestions that Newton gives you, it may take you a while. So just try to understand the idea. In this case, same thing. We really, well, in this case, we cannot say that we plug in 0 for x, but since both f and g are assumed to have a limit, we can, and square root is a continuous function, we can pass the square root outside of the limit and then kind of distribute the limit to each of these expressions. So your final answer will pretty much be just this, even though, well, I shouldn't call it f of 0. It's the limit of the function at 0. But again, with that disclaimer, I guess we can write it f of 0. But let's just be careful. We don't evaluate the function at 0. We just kind of throw in 0 and checking out the limit. And here we have 6g of 0. Same thing, right? This is the limit at 0. And limit of 0 of f is given to be 5. So we can just erase that. And limit of g at 0 is equal to 6. So we can just plug in 5 here and 6 here. So 36 plus 15 is 51. I forgot the square root, of course. Well, hopefully this time it is correct. I guess lesson learned, don't make typos. 48 plus 15 is 63. So it's not going to give me, I don't think it's going to give me another chance here. So I might have to redo this problem. It's going to set me back a little, but not a big deal. This one is even easier because we don't have a radical. But the idea is the same. So we're just going to plug in -6. When you plug it into f, you get 3. And when you do it for g, you do -7. So technically, what we do is called using the properties of limits. But at this point, it doesn't really matter how we get this done, as long as we get this done. At the end of Calculus 2, it just doesn't matter how you find limits. And most likely, you'll just be able to use technology. So we're trying to be as efficient as we can. This is a rational function. And again, the first instinct is to throw -3 right in there. And following the first instinct, I am setting up this expression and I'm going to evaluate it. So in the denominator we have -7, and in the numerator we have 81 plus 15, 96. 96 plus 7 is 103. And of course it's negative, and I hope I'm not making a mistake. We don't need no other setbacks, and this is right. So remember, we're practicing the idea of plugging in the target value into the function as an instinct, right? And then figuring out what to do next. In this case, we have same kind of thing, right? So there's nothing wrong with the instinct of putting things in to the function. Like in this case, it doesn't matter if it's 4 approaches from the left or from the right, so we're just going to be careful what we're plugging in. So when I plug in 4 from the left, it's like I'm plugging in 3.99999 minus 2 an absolute value. And what happens here? Something that approaches to 4 minus 2, it's something that approaches to 2, and absolute value of that is just 2. And what happens when I do it with 4 plus? Nothing really happens. You're just going to be plugging in some number that is slightly greater than 4, but it's still going to be close to 4. So when you subtract 2, it's close to 2, and absolute value of 2 is still 2. So both of these answers are 2 and 2. But most importantly, it's because this function is continuous, so when the two-sided limit exists, both one-sided limits exist as well. I think this problem may be slightly different, but let's practice this reflex. X approaches to -1 from the left of square root of 3x plus 3 minus 5. So we're going to plug in something from the left. So we're plugging in -1.0001. So we're getting something that is less than 1. Then we plug in, when you multiply it by 3, you get something that is slightly less than 3. And when you add 3, you get something that is slightly less than 0. So when you take a square root of that, square root of a negative number does not exist. So you see how we don't really need to do much here because we know this limit doesn't exist. And that's it. When we plug in a number slightly greater than -1, let's say we plug in 1.0001, so we multiply it by 3, it's negative, so we get something slightly this is wrong, right? So we're not plugging, so it was negative to begin with, so it's negative 0.999. When you multiply it by 3, you get something, it's going to be 2.99999 plus 3, you get something that is slightly greater than 0. So when you take a square root of that, it's 0, and you subtract 5, you end up with -5. So that's the difference between the left-sided limit and the right-sided limit here. So the first one does not exist, and the second one is equal to -5. And we can easily verify everything that we do here with Desmos, right? So all we have to do is just graph this function, and you will see that this function to the left of -1, it doesn't exist, therefore there is no left-sided limit, and to the right of it, it approaches to -5. So very easy to verify. All right, so let's go to the next question. I'm going to just copy this over. Let's see if it's going to let me. Oh yeah, it did. So in this case, we trying to plug in -2. So -2 times -4, it's 8. 8 minus 8 is 0. But since we take the square root, we need to be careful here. When I take the number -2 from the left, it's -2, 0.01. So multiplied by -4, it becomes 8.004. When you subtract it from, or when you subtract another 8 from it, you get 0, something slightly greater than 0. Square root of 0 is 0, and 0 plus 3 is just 3. And when you're plugging in -2 plus, it's a -1.999. When you multiply it by -4, it becomes 7.99 something. Minus 8 will give you a negative number. So square root of a negative number doesn't exist. So the right-sided limit in this case does not exist. So this is 3 and this is an empty set. In this case, we can, well, I can tell you right away that since square root of 4x plus 4 is a continuous function, evaluating the limit of it is just the same as plugging in -1. So when you plug in -1, the answer is 0. So that means it doesn't matter if it's a plus or minus here, the answer will be 0. So both of these answers are zeros. So this idea that that's a fun app to play with. This idea of plugging in the input into the function works regardless of the type of the function present in the limit. So even if you have a trigonometric function, you should still try to plug in the target value into the function just to see what happens. And in this case, we have pi over 6, so we have tangent of -pi over 3 minus sine of pi over 3. And that seems like to be a well-defined expression. Sine of pi over 3 is... what's sine of pi over 3? It's square root of 3 over 2. And tangent of -pi over 3, it's the negative square root of 3 over 2 over 1/2. So the answer is -√3 minus square root of 3 over 2. So it's just -3 over 2. This one is when we finally get to use the special limit. And before we even recognize the opportunity to use the special limit, let's see what happens when you throw 0 into the function. You have 0 plus cosine of 0 minus 1 over 0. So we have, what do we have here? We have 0 plus 1 minus 1 over 0, so it looks like this is 0 over 0, which is in one of the well-known indeterminate forms. So what do? Well, in this case, normally we would acknowledge that it's an indeterminate form, and in the future we would probably use L'Hopital's rule. But in this case, there is a way out of this uncertainty by recognizing this special limit right over here, this one. So remember, 1 minus cosine x divided by x is equal to 0, and it's true for anything. So 1 minus cosine of anything divided by anything, as long as that anything goes to 0, will be equal to 0. So let's remember that. And in this problem, we're going to have to do the following. We're going to separate the problem into two. And you see how here, now that we have two problems, as x approaches to 0, this part, since x is just cancels out, this part just approaches to -1/2. Now, this part really looks like a special limit, but in the special limit, it has to be a perfect match, right, with what we have inside of the cosine and what's in the denominator. We don't have a perfect match here. Here we have 7, and here we have 2. So what do we do with it? What we do with it is we can simply remove this 2 by just taking it out. So we don't have 2 anymore. Let's just take it outside of this expression. And we can easily bring 7 over here. We can easily bring 7 over here if we just multiply by 7 over here. Now that we have a perfect match between what's inside of the cosine in the numerator and what's in the denominator, now we know that this whole expression as a function goes to 0 because now we use the special limit. So the final answer would be what? This part went to -1/2, and this part went to 7/2 times 0, which is still 0. So the final answer is -1/2. And again, we can always check this using graphing approach and simply graph this function. And if you look at this function, the graph looks pretty cool. And we're looking at 0. At 0, this function approaches to, you can see that it's -1/2, right? So, which is pretty cool. Right, we learned that analytically. So before you submit the answer, you can always kind of check your work. Here we have a limit as x approaches to pi/3. Make sure that you don't try to bust out a special limit when the target value is not 0. So again, the instinct should be to throw the target value first. Don't assume anything until you try to evaluate your limit at the given target value. In this case, we have cosine of pi over 3. Cosine of pi over 3 is 1/2. And tangent of pi over 3, it's 1/2 over square root of 3 over 2. So the final answer would be -4 over square root of 3 in the numerator and -5/2 in the denominator. So simplifying it gives us what, 8 over 5 square root of 3. We can simplify this, but the problem doesn't ask us to simplify anything, so we just write it like this: 8 over 5 square root of 3. Great. Let's see, what are we doing wrong here? Tangent of pi over 3 is 1/2 over square root of 3 over 2, so it's 1 over square root of 3. Cosine of pi over 3 is 1/2. -3 maybe it does want us to simplify it. So I'm gonna, well, two things I want to do here. I want to show you that when it now became like really important for me, I'm actually going to double check my answer with technology before I put it for the next time, just to confirm that what I'm doing is fine. So let's just visual appeal, put negative over there. So this is my function, right? We're looking at this function at pi over 3. So let's just throw pi over 3 in there, right? So the function is continuous at pi over 3. So we can actually try to find pi over 3. So it's right here, right? So my limit is pretty much 2.771. And now I just want to make sure that, let's enter my first answer. So that answer was clearly wrong, right? So 0.92. So I guess I did make an arithmetic mistake somewhere. Let's see where. 1 over red 3, so -4 over radical 3. -3 plus 1/2. Now I'm insecure about my arithmetic skills. This is true. And now what are we doing here? Negative 8 over something is it's not clicking here. 8 square root of 3 over 15, that's the same thing, right? I'm not doing this the right way. I need to get this evaluated at pi over 3. Why am I not getting this answer? Tangent of pi over 3 is, oh my god, I put cotangent. This is what I computed here was cotangent. So tangent, to find tangent, we do sine of pi over 3, which is square root of 3 over 2, and then cosine of pi over 3 is 1/2. So what this should be is root 3. So this is just -4 root 3, and then now we got everything in order. We're going to do it's 8 root 3 over 5, but I'm still going to check my work here, right? So we expect the answer to be this number right here, but And now we got that number. So 8 root 3 over 5 is the right answer. So it was just a typo, which inevitably will happen to anybody doing homework. Let's see what we got. And that one is right. So again, let's not forget what we're practicing here. We're practicing the idea of substituting the target value into the function right away without any hesitation, and then figuring out what's going on. So next question is another limit, x approaches to 0. Here we're doing cosecant. If you try to evaluate cosecant at 0, you're gonna get 0. Or not. Cosecant at 0 is undefined. So technically, well, we do say it's undefined, but technically it's like kind of plus or minus infinity over plus or minus infinity. So it's one of those indeterminate forms. We can continue to be confused by this, but instead, what we can do is we can rewrite cosecant as a sine. So this will be 1 over sine of negative 4x, and this will be 1 over sine of negative 6x. And we can further simplify it using the properties of fractions. So we end up with sine of negative 6x divided by sine of negative 4x. And in this case, we now have 0 over 0. So we can remain confused by this indeterminate form, or we can recognize the opportunity to use one of the special limits. And how would we do that? Well, we throw, let me remind you what that special limit is. It's this one right here. So basically it says sine of anything divided by anything, as long as that something goes to 0, will be equal to 1. So my handwriting gets bigger and bigger here. So if I throw negative 6x here, then the numerator now is negative, it's just 1. If I throw here negative 4x, then now the denominator is also 1. But I can just throw negative 6x in here. To compensate for that, I'm going to put negative 6x over here. And to compensate for that negative 4x, I'm going to put negative 4x over here. So what we have here now is the limit of negative 6x over negative 4x. X's cancel, and we end up with simply 3/2. This is not a surprise at all. We would have learned that from just looking at the graph. Let me show you. We could have learned the same thing by simply looking at the graph of this function. Cosecant of negative 4x divided by cosecant of negative 6x. X approaches to 0, and even though at 0 the function is undefined, we can see that here, but as you approach to 0, it is 1.5, which is 3/2. All right, great job. This is another one of those limits where we just follow the reflex, and the reflex is to evaluate the function at the target value. So it doesn't mean it's easy though, right? So the idea is easy. Executing the idea still could be hard, but we do throw the pi over 6 inside, and the feeling here is that the function should be continuous at that value. So all we have to do is just simply evaluate the function. So cosine of negative pi over 6 is root 3 over 2. Tangent of negative pi over 6 is sine of negative pi over 6 divided by cosine. So sine of negative power 6 is 1/2, and cosine is √3/2. So we just need to simplify this. Negative 3 √3/2 minus, or rather plus here, plus 4 divided by √3, but rationalizing the denominator, and I'm like, I don't want to find the common denominator and all that stuff, so I'll just enter it like this. Minus 3 radical 3/2 plus 4 radical 3/3, and it should accept it if it's right. Yep, that's very nice of Newton to accept this answer. So we're moving along. That's going to be a fun limit. We have I thought it was going to be a fun limit, but again, remember, your first instinct is to throw the target value inside. So it would have been a fun limit if it was 0, and instead of 5 we had 8, but no, now it's not. So we're putting -4 sine of -π/3 divided by -8 plus 5 cosine of -π/3, and as long as you know what sine and cosine of -π/3, you pretty much set. So -4 √3/2 -8 plus 5/2. And since it's Newton, we don't have to simplify it, although the numerator does simplify a bit. And in the denominator, what do we have? -8 plus 5/2. Let's see if it will accept that answer. Of course it does. Good job. We've seen a problem like this before, right? And now that we have seen it, we can be a little bit more efficient this time. So how can we be a little bit more efficient? Well, we're going to apply the reciprocal identity here and rewrite this as sine of 10x divided by sine of -6x. But remember, sine of 10x, as long as 10x goes to 0, acts like 10x. Same applies to sine of -6x. So this whole thing can be simplified just to the following number, which is -5/3. It's okay to use shortcuts sometimes in Calculus 2 to do pre-calculus or algebraic tasks. In general, if we were in pre-calculus class, I wouldn't recommend you this approach, but in this class, that's totally fine. We also have seen this problem. We've seen this problem before, so we can also be efficient. We can recognize this problem right away, and we can start separating this function. I feel like we've seen this exact problem. I don't want to scroll, but what do we do here? We take this -2, or we can just take the 2. We can keep the negative. So we can take that 2 out. But now we need to match this denominator to what's inside of cosine. So I'm going to throw 5 in here, but to compensate for that 5, I also need 5 over here. And now the denominator and what's inside of cosine matching, and it goes to 0. So this whole thing goes to 0 as one of the special limits, and this in this part, once you cancel x, you just end up with -5 halves. So the answer is -5 halves plus 0, which is just -5 halves. And I think we're done with this homework, as we achieved 100% mastery. Again, this was not the best homework to practice the infinite arithmetic approach, but there are just too many problems on covering this exact skill, so we practice what we have. If you have any questions, please do not hesitate to reach out.